SwayamPrabha. Digital India. Educated India.
Hello friends, I am Prashant, I am TA for this course, and this course deals mainly with the experimentation which we do for aircraft, determining what will be the angle of deflections of control surfaces, how to determine center of gravity, neutral point, climb rate, and how to determine what will be the CD of aircraft, drag, CD naught, various different things through experimental process. Today what we will be studying will be the calibration of control surface. Now before going deep into this topic, first let us understand what calibration means or why we do calibration. So as you know, calibration is configuring your result or output for a sample within a prescribed limit. For instance, if I want to sample my angle or deflection in the scale of voltage from 0 to 5, now I have to calibrate that control surface. And why we need this sort of calibration? Because as you can see in an aircraft, as per your stick control, you can maneuver your control surface, whether it be aileron or elevator. So why do we require calibration for these control surfaces? As long as we are considering mechanical systems, you can directly control it, we are giving required input. But once your data acquisition system comes into play or you go for electronic circuit, it will give you output in terms of voltage and current. Thus, we have to calibrate your system according to what voltage your deflection has been given, or you have to map what will be deflection corresponding to your particular voltage. So that's why we need calibration of control surface. So for this topic, what will be the experimental setup or what will be the instruments required will be, first you need an inclinometer. Second will be your potentiometer. Third will be your data acquisition system, and we are using an NI data acquisition system, so NI DAC. And for seeing the results, you need a computer or a output device. Here we are using laptop or PC, anything you can see the result. Now these are the instruments which will be requiring for, and also a software for interfacing. Software for interfacing. Now I will be explaining each part, what does each part measure or what does each part contribute to our experiment. Now first we'll be going with inclinometer. As the name suggests, it has something to do with inclination. That side, that inclinometer will give you what will be the angle, tilt, elevation or depression of a particular surface with respect to gravity. So inclinometer will basically give you what will be the angle, whether it's a positive, this is negative slope, so your angle of depression, or angle of elevation, or a neutral, means it doesn't have any slope. Now we in the experiment we have two different inclinometers. Now this being a digital inclinometer, as you know, digital instruments are quite accurate, so the accuracy of this digital inclinometer is quite high. And whereas this is your analog inclinometer. As you can see, while tilting this instrument, the needle indicates what particular angle it has been tilted. This represents your inclination or positive or negative slope. Now, as you know, this is analog device, so the accuracy is not as high as that of a digital inclinometer, but earlier days this was used for determining your angle or slope. Now, the second instrument which we require is potentiometer. Now, potentiometer is very simple device, and also as you can see, the name suggests potentiometer, it has to do something with potential or voltage. You can imagine, or as you can say, is a 3-terminal device A, B, C, a 3-terminal device, and it has a rotatory contact which varies, which act as a potential divider between these two terminals. You can vary your resistance according to that contact switch, and your potential will vary according to that sliding mechanism. A simple circuit of potentiometer can be represented by a 24-volt DC supply. Suppose we are having this is your resistance R1, your R2, this is your contact, this is your load resistance RL. You have to determine what will be the voltage across this load resistance, which will be equal to, if we further simplify this circuit, R1, say this is R2, so that I can differentiate this R2 with this R2, and your load resistance RL. So the voltage across this load resistance will be the voltage across this VL, which can be determined using formula. The equivalent resistance between these two will be R equivalent equals to R2 RL by R2 plus RL. Now this will be modified as R1 by R equivalent. So voltage across this resistance will be V equivalent equals to I into R equivalent, where I will be I equals to this volt 24, or let me write this equals to VDC divided by R equivalent plus R1. Hence, my VL will be VDC upon R equivalent plus R1 into R equivalent, which is equal to VDC divided by R2 RL by R2 plus RL plus R1 into R2 RL by R2 plus RL. Further simplifying this, we will get VDC upon R2 RL plus R1 R2 plus R1 RL into R2 RL by R2 plus RL divided by R2 plus RL. This and this will get cancelled, and your voltage across that load resistance will be VDC into R2 RL divided by R2 RL plus R1 R2 plus R1 RL. So as you can see by this particular equation, the voltage across your load resistance can be varied by varying this value of R2. If value of load resistance is very high, then you can simply write this equivalent to R2 upon R1 plus R2 into VDC. So just varying this resistance using contact switch, you can directly vary the potential across your load resistance. So that principle the potentiometer is using to determine what will be your voltage against the deflection of control surface. We will be coming to that when we will be discussing your experimental part. Now these two we have already discussed, and I told we require a data acquisition system. Data acquisition system we are using is our national instrumentation, this NI, and as the NI, we can simplify that data acquisition system as an NI module. All the sensor data will be coming into NI module. This NI module is powered by a power supply. Now the output of this NI module can be seen in your laptop or PC, and obviously you cannot directly access your NI module, so you need the interfacing software. Here we are using LabVIEW. This is a basic block diagram for calibration of control surface. We have discussed about your full system, what will be required for your calibration of control surface. Now let's see what is the process for determining what calibration of your control surface. Now the procedure involves, you have to first mount your inclinometer on the control surface, for which you want to measure or calibrate. Once this inclinometer is mounted on that device, you have to secondly determine reference point. Now what do you mean by reference point? Suppose this is your wing. This is a 2D section of a wing, and you have a control surface somewhere around here. This inclinometer will be mounted on this particular control surface for which you have to do calibration. Now as you can see, this is not, suppose this is your ground, this is not exactly parallel to ground. So by default your inclinometer will be giving you some reading. Say suppose for this particular instance it's giving you minus 10 degree. So your default or reference point without any deflection, this is when your control surface has not been deflected. Suppose this is your wing, this is your control surface, it has not been deflected, then this represents your reference point. So say for this particular degree, your voltage corresponding to this is 3 volts. Now this particular reading you can, while we will be performing your experiments, you can see how this readings are calculated using LabVIEW program. So this is your reference point. After setting reference point, third process is you have to set this reference point as 0 degree. So for 3 volts, your deflection will be 0 degree. Now, in order to calibrate your control surface, the fourth step involves to deflect your control surface on a positive side and a negative side. So, if this is your wing section, positive means you have to deflect this upwards and calculate this angle using your inclinometer angle. This is for positive deflection. Similarly, for negative deflection, you have to calculate angle. You have to note that angle using inclinometer, it will be mounted here, and corresponding to that, using VI program, you will be able to get voltages. Voltages for different angles deflected on both sides with some interval. That is, I have already set my reference point, and after that you have to deflect that in positive side and negative side with some interval. Say with 1 degree, what will be the corresponding voltages you have to measure and make a note of that. After performing this particular steps, you will get a chart which will be voltages and deflection. Voltage, deflection. So, for instance, for positive deflection, suppose I get a voltage of 4 volts with deflection of 10 degree and 3.8 with deflection of 9 degree. Similarly, for 0 deflection, I already told you, suppose it was 3 degree. Now, while deflecting on different side, your reading will be for -1 degree, suppose your voltage is 2.8 volts. And similarly, -10 degree, your voltage is say 2 volts. So you get a chart with voltages and deflection of control surface. Now, since we are assuming that this is a linear variation, the deflection of control surface with voltage is a linear variation, so we'll plot your voltage versus deflection will give you positive, negative, will give you a line of sort y equals to mx plus c, where m is your slope, c is your intercept, y represents your voltage and x represents your deflection. So from this calculation or this particular readings, you will be able to calculate what will be the value of m, what will be the value of c. As you can see, for x equals 0, that is 0 deflection, y will be your c, and voltage in this case will be 3 volts. So this will be 3 volts. Similarly, now giving different values of deflection, you know already c, you know the value of y, you can determine m. This is one process to determine what is the relation between your voltage and deflection. There is another way to determine what will be the relation of voltage and deflection of control surface. Now, suppose you don't have instruments such as digital inclinometer. then in that case, what can be approximate way to determine what is the relation between voltage and your control surface deflection? Now, we don't know what is the deflection of control surface. These were the readings which we determined from using this inclinometer, distal inclinometer and log inclinometer. Suppose we don't have any of that, and suppose the control surface is too small to mount that inclinometer. Then in that case, there is an approximate way to determine what will be the angle of deflection. Suppose this was your wing and you deflected your control surface to some degree, say theta. This is theta. Now you want to know what is the angle of this. Since we are assuming this is a uniform control surface, means the thickness doesn't vary, so we measure what is the distance between, what is the width of this control surface. Say W is the width of this control surface. That means this is W. You can also calculate, or you can also measure what was the distance of this particular deflection from your equilibrium point. This was my wing, this was my equilibrium point, what was the distance, say h. So you know h, you know this, because this will be always constant since this is of uniform width, and also this width doesn't vary changing your angle. So you can calculate what will be the angle between, what will be the angle of deflection using sin theta equals to h by w, where you know w, you know height, so theta will be sin inverse of h by w. So you can approximate, or you can develop an approximate relation between voltage and deflection. Now I am saying this approximate because the result may vary. Suppose for this 10 degree you are getting 4 volts. For this you might get somewhat like 13 or 12 degree you will get 4 volts. It can vary according to that. But this is a good approximate way to calculate if you don't have such instrument or the surface is too small. This is a good way to approximate what is the relation between voltage and deflection. Now earlier I discussed why did we need calibration. Once we did calibration, we got voltage and deflection. So where we want to apply that? So let's see some application where this calibration will be needed. Now throughout this course, you will be seeing various datas that will be, suppose, for calculation of angle of attack, alpha, beta, slight slip angle, as well as what will be the deflection of elevator, your aileron and your rudder. So these all are the quantities which you want to measure, but I told before also that when a digital system or electronic system is involved, you can only get output in terms of either voltage or current. So that's why this voltage, for determining what will be the deflection of this particular control surface or what will be the angle of attack or side slip angle, you need to have a relation between voltages, current and these physical parameters which you want to measure. So that's why we need calibration of control surface, not only control surface, different calibration we need, even for angle of attack, even for calculating slight slip angle, different we require a relationship between them. And since once calibration is done, that is, you have found a relation, assuming that the control surface deflection and voltage were a linear relation. Once this constant and the slope is determined, while taking data, you will be only, if no interfacing or software or coding has been done, then you will only get what will be the voltage for some deflection. For some deflection, that deflection you want to know, because as you know, in aerodynamics of an aircraft, you require different parameters. What will be CL delta A, what will be CD delta A, or CL delta E. Means you require a relation of delta E. So you will be getting only voltages, and since you know the relation what is M, what is C, you can determine what will be your deflection using this M and C value. So for this experiment, we have derived what is relation between voltage and deflection. We'll be seeing that while we're performing experiments live. Then you can see what were the assumptions we took, how to determine reference point, how to deflect surface, and what voltages we are getting. Thank you.